I would like to S. Ramashankar. He is a BSc third year mathematics student from the American College, Madurai, Tamil Nadu. So, Ramashankar, you can start your session.
Good evening, everyone. Now we are going to see about dimension of the sum of subspaces. Okay. Before going to see, we just saw some basic definitions and examples. Then we go to the theorem and proof of the statement. Okay. Basis is nothing but a non-empty subset S of a vector space V is a basis if the set S spans V and the set is linear independent. Okay. Then what is the dimension of a vector space? Can anyone say that what is the dimension of a vector space?
The number of elements in the basis?
Yeah, that's correct. Dimension of a vector space V is a number of elements in a basis of V. That is dimension of V equal to cardinality of basis of V. Okay. Now, then the basis extension theorem. That is nothing but if we have the linear independent set in some vector space, linear independent set, if we add some more elements, we can add some more elements and we can make it a basis of the vector space. That is called as the basis extension theorem. Now see the statement of the basis extension theorem. V be a vector space of the dimension n and W be a subspace of V. Any basis of W can be extended to form a basis of vector space V. Now I am not going to prove it. That's I state the theorem. Let's go to the examples. Let's take a vector space R2. Can anyone say the basis for R2?
Zero 110.
1001.
Yes, the standard basis of R2 is 10101. Then what is the dimension of R2?
2.
2.
Yes, that's 2. Now let's take a subspace as x-axis. Okay, then can anyone give the basis for x-axis W1?
10.
The dimension of y-axis is
1.
1. Yes. Okay. What is W1 intersection W2? Can anyone say what is W1 intersection W2?
Origin 0. 0 0.
Yeah, it's a 0 vector. Then okay, now what is the dimension of 0 vector? That is W1 intersection W2.
0.
Yes. How do you think how you say the 0 as a dimension of the 0 vector?
Because by contradiction, if there is any element in its basis, then immediately we can actually not sure. I'm not sure.
Okay, then how can we how you say the one set as a basis of the vector space when you say the set?
So maximal linearly independent set.
Yes. Otherwise, we can say the two condition. The set S non-empty set is linearly independent and we need to be spans the vector space, right?
Yes. But if there's any element, then it will immediately span like an entire line.
Yes.
Therefore, it cannot be, dimension has to be 0.
Yes. That is, we can say like this, because zero vector, in zero vector, it is not, singleton set zero vector is not a linear independent set. Therefore, basis of zero vector is a empty set. Therefore, dimension of empty set is 0. Okay. Now, W1 plus W2 equal to, can anyone guess what is W1 plus W2?
W1 by x-axis and W2 is by x-axis.
Yes, W1 is x-axis, okay. I am asking what is W1 plus W2?
R2.
Yeah, that is R2. Therefore, the dimension of W1 plus W2 equal to 2 and dimension of W1 equal to 1, dimension of W2 equal to 1. Therefore, dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2 equal to 2. Here we can see some relation, right? These two are equal. Then we can say that dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Right? For this example, let's consider another example. Now, let's consider a vector space M3 of R. Can anyone, this is the basis for the M3 of R, right? Then what is the dimension of M3 of R?
9.
Yeah, that's 9. Now, let's consider a subspace of M3 of R as a upper triangular matrices. Then what is the dimension of W1?
6.
Yeah, that is 6. And similarly, let's consider W2 is a lower triangular matrices. Then dimension of W2 equal to?
Again 6.
Yeah. What is W1 intersection W2? Can anyone think it?
The diagonal
Yes,
matrix.
Yeah. W1 intersection W2 is a diagonal matrices. Therefore, what is the dimension of diagonal matrices?
3.
Yeah. 3. Now, let W1 plus W2 equal to this. Then what is W1 plus W2?
Set of all 3 cross 3 matrices over R.
Yes, that is nothing but M3 of R.
Yeah.
Okay. Now, dimension of W1 plus W2 equal to 9 and dimension of W1 equal to 6 and dimension of W2 equal to 6, dimension of W1 intersection W2 equal to 3 and dimension of W1 plus dimension of W2 minus dimension of W1 intersection of W2 equal to 9. Here also the dimension of W1 plus W2 and this equal to are same. Therefore, we can say this. Is it true for every two subspaces of vector space? Let's prove it. My statement is V be a vector space and W1 and W2 be a subspace of V, then dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Okay. First, let's consider this set S12 as U1, U2 up to UK be a basis for W1 intersection W2. Then dimension of W1 intersection W2 is
K.
Yeah, very good. That is K. And we know that W1 intersection W2 is the subset of W1 and W1 intersection W2 is a subset of W2. By
Ramsankar,
basis section. Yes, sir.
Ramsankar, did you assume that W1 and W2 are finite dimensional?
Yes, sir. I need to mention it. Okay, sir.
Yeah.
Here, here V is a finite dimensional. We are assuming that V is a finite dimensional vector space. Therefore, the W1 and W2 are also finite dimensional because subspace of vector space W1 W2. Therefore, it is also finite dimensional. I forgot to mention it. Okay, sir. Thank you. Now, by basis extension theorem, we can extend the basis of W1 intersection W2 to form a basis of W1 as well as W2, right? So, let S1 equal to U1, U2 up to UK and V1, V2 up to Vm be a basis of W1. Then dimension of W1 equal to
K plus M.
that is K plus M. Let's assume S2 as the U1, U2 up to UK and W1, W2 up to Wn be a basis of W2. Then dimension of W2 be
K plus N.
N. Yes. Then dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2 equal to K plus M plus K plus N minus K. That's equal to K plus M plus N. What we are trying to prove? The dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2 equal to dimension of W1 plus W2. Therefore, enough to prove dimension of W1 plus W2 equal to K plus M plus N, right? That is to prove the W1 plus W2 basis of W1 plus W2 contains K plus M plus N elements, right? I'm taking S, the set S contains K plus M plus N. I need to prove S is a basis for W1 plus W2. How to prove S is a basis for W1 plus W2? Can anyone say how to prove S is the basis for W1 plus W2?
We have to show that it first spans the set and also it is linearly independent.
Yeah, that's correct. You need to show S spans W1 plus W2 and S is linearly independent. First, let's prove S spans W1 plus W2. How to prove that S spans W1 plus W2?
We take an element from the set and we see if we can write it as a linear combination of S.
Yes. That we can say that is the L of S equal to W1 plus W2, right?
Yes.
How to show L of S equal to W1 plus W2?
Subset of each other.
Yeah. We need to show L of S is subset of W1 plus W2 and W1 plus W2 subset of L of S. First, let's think what is L of S. Can anyone say what is L of S?
Yes. Set of all the finite linear combination of the set S.
Yes. More precisely, you can say something.
Set of all finite linear combination of the set S. That is L of S.
More we can say something. L of S is there. Can anyone say that? Yeah, okay. I will say L of S is the smallest subspace containing S, right? Did you get it? L of S is the smallest subspace containing S, and here W1 and W2 are subspaces. Then W1 intersection W2 subspace, and W1 plus W2 is also subspace. Therefore, W1 plus W2 is subspace containing S. But L of S is the smallest subspace containing S. Therefore, first one is clearly true, right? Did you convince yourself?
Yes.
Yes.
Okay. Then we need to prove second one. W1 plus W2 subset of L of S. How to prove a set subset of one set is a subset of another set?
we will take any element in W1 plus W2, and then we will find the real number such that the finite linear
No.
combination. Huh?
Oh yeah, yes, correct.
Yeah.
I am asking for subset. How to prove if A subset of B? How to prove A subset of B?
Yeah, we will take an element in W1 plus W2. Then we will show this lies in L of S.
Yeah, that's correct.
Yeah.
And we need to take one element. I take x belongs to W1 plus W2. I need to show x belongs to L of S. Okay. Then if x belongs to W1 plus W2, then there exists W1 in subspace W1 and W2 in subspace W2 such that x equal to W1 plus W2, right?
Yeah.
Yes.
S1 is the basis for W1. S2 is a basis for W2. So element of W1 can be written as the linear combination of S1, elements of S1, and element of W2 is a written as linear combination of element of S2, right? Therefore, W1 can be written as the linear combination of alpha ui plus linear combination of beta j vj because S1 spans W1. Similarly for W2. Then x equal to W1 plus W2 that equal to linear combination of alpha I plus gamma I of ui plus linear combination of beta j vj plus linear combination of delta j wj, right? Now look x. This looks like the linear combination of elements of S. U1 U2 and V1 Vm and W1 Wm. See that x equal to linear combination of ui and vj and wj. Therefore x is the linear combination of element of S. Therefore x belongs to L of S. Did you get it?
Yes. Can you please show the previous slide again?
Yes. S equal to U1 up to UK and V1 up to Vm and W1 up to Wn, right?
Yeah.
And x is x equal to linear combination of these elements. Therefore, we can say x belongs to L of S, right? I take the element x in W1 plus W2 and I showed it x belongs to L of S. Therefore, W1 plus W2 subset of L of S, right? We already proved L of S subset of W1 plus W2. Therefore, L of S equal to W1 plus W2. Now, we proved S spans W1 plus W2. Now, we need to prove S is linear independent. How to prove S that S is linear independent?
We have to show there exists a non-zero element such that this is 0. This combination is 0.
No, you are saying for the linear dependent.
No, I'm saying. Oh, sorry. Yeah.
I'm asking for linear
All the
independent.
coefficients are equal to 0.
All the coefficients are 0. Yeah.
Yeah, we need to show all the scalars are 0. To prove, we need to show all the scalars are 0. Okay. Now the equation 1 implies that linear combination of alpha u plus linear combination of beta j vj equal to minus of linear combination of gamma or wr. Subtracting this in both side of the equation, we get this. Now see that LHS of the equation is in the form of elements of S1, U1, U2, UK and V1, V2, Vm. Then LHS of this equation belongs to W1 because S1 is the basis and it is a linear combination of elements of S1. Then LHS of the equation belongs to L1, W1, right? And RHS of the equation it is in the form of linear combination of elements of S2. And S2 is the basis for W2. Then RHS of the equation belongs to W2, right? RHS belongs to W2 and LHS belongs to W1. Is anybody have doubt here?
No.
Okay, if you have doubt, then think about it. Okay, now here RHS equal to LHS, right? This equal to this. Therefore, and this belongs to W2, LHS belongs to W1, and this belongs to RHS equal to LHS implies what this RHS belongs to W1. The linear combination of minus of gamma R WR belongs to W1, right?
Yeah, right.
Yeah. Then it belongs to W2 and it belongs to W1. Then it belongs to W1 intersection W2, right?
Yes.
Is anybody have doubt? Okay, then I will move to the next slide. And here, the minus of linear combination of gamma WR belongs to W1 intersection W2, and S12 is the basis of W1 intersection W2. Therefore, every element of W1 intersection W2 can be written as the linear combination of elements of S12, right? Therefore, this belongs to W1 intersection W2. It can be written as the linear combination of element of S. I'm taking minus of linear combination of gamma WR equal to linear combination of delta I UI, because S12 spans W1 intersection W2, right? Now adding linear combination of gamma UI, adding gamma WR, linear combination of gamma WR in both sides of the equation, we get this, right? Now see here, it is the UI and WR, I equal to 1 to K and R equal to 1 to N. Now see the S2, it is the elements of U1 up to UK and W1, W2 up to WN. It is a basis of W2. Therefore, since it is a basis, it is linear independent, right?
Yeah.
Then what we can say from this?
All the delta i's and gamma r's are 0.
Yeah, that's correct. All the squares are 0 since S2 is a linear independent set. Now, all the squares are 0. All the gammas are 0. That implies summation of gamma R WR equal to 0, right? Because every gamma R equal to 0, then summation also becomes 0. Did you get it?
Yes.
Yes. Okay. Now by 1, what is our equation 1 is this. Here, this part becomes 0. Then remaining 2 part, we need to prove, we proved that all gamma R is 0. We need to prove all alpha and beta j equal to 0. Let's try to prove it. Then by equation 1, we can return that. We can return this. Here, I equal to 1 to K UI and j equal to 1 to M dj. See the set S1. Here U1 up to UK and V1 up to VM. Therefore, here S1 is a basis of W1 and S1 is linear independent. And what we can say that this equal to 0, then we can say S1 is in the form of linear combination of elements of S1 and S1 is the linear independent. Okay, we can say yes, that's correct. Every scalars are 0. Since S1 is linear independent, every scalars are 0, right? Is anybody have the doubt in this? Okay, then I will move. Now we proved that here every alpha I are 0 and beta j equal to 0, and in the previous we proved every gamma r equal to 0. Then we proved all alpha I gamma j, all alpha I beta j gamma r equal to 0. Therefore we proved S is the linear independent set. Already we proved S spans W1 plus W2. Therefore S is a basis for W1 plus W2. We proved it. Therefore we can say that dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2 plus dimension of W1 intersection W2. Right? Because W1 plus W2, basis of W1 plus W2 has a k plus m plus n elements. And we proved it. Now, we proved it for the two subspaces. Did you see this equation before anywhere, in any of the places?
Yeah, in set theory we have a similar formula.
Yeah. Where? Can you see?
Yeah, in set theory.
In set theory, what is the formula?
For A union B, n of A union B, we take n of A plus n of B
Yes,
minus
yes.
n of A intersection.
That's correct. Yeah, that's n of A union B equal to n of A plus n of B minus n of A intersection B. We proved it for the sum of two subspaces. Is it true for more than two subspaces? That is, we need to check this is true. Think about this, n of A union B. Similarly, n of A union B union C, we write n of A plus n of B. Similarly, for this, is this true? We need to check also. Here, V equal to, I am taking vector space as R2 and W1 as x-axis and W2 is y-axis and W3 is y equal to x line. Then W1 intersection W2 equal to 0 vector and W2, similarly W2 intersection W2 equal to 0 vector and W1 intersection W3 equal to 0 vector and W1 intersection W2 intersection W3 equal to 0 vector. Here, what is W1 plus W2? What is W1 plus W2 plus W3? Okay, that is nothing but that is R2. Therefore, dimension of W1 plus dimension of W1 plus W2 plus W3 equal to 2 and this equal to 3. Here, this not equal. We can say it is true for only two subspaces. More than two subspaces, it is not true. Right? Did you understand this? Okay. Then, okay. Thank you, sir. Thank you, everyone. Thank you for the opportunity for presenting in career. Thank you.
Anyone have any question? Okay, Ramsankar, you said that the basis of singleton 0
Yes, sir.
is empty set. How will you prove
Yes,
that?
sir. We first of all, basis is the basis. Need to satisfy two conditions. That is linear independent and it need to spans 0 vector. It need to spans the vector space. But in 0 vector, there is only one element. But if you take the element, it is not a linear independent set. Therefore, the basis contains no element. Therefore, basis must be a empty set.
Okay. You proved in the result that LS is a subset of W1 plus W2, right?
Yes, sir.
Which definition you use?
The definition of L of S, sir. L of S is the least subspace containing S.
Okay. So what is the least subspace containing phi?
0 vector.
Singleton 0, right?
Yes, sir.
So its span of phi is singleton 0.
Full of. Yes, sir.
And phi is independent set.
Yes, sir. We need to.
It satisfies both the condition.
Yes, sir.
Okay, moving on to the next presentation.
Yeah. Sir, one thing.
Yeah.
Ram, the
Yes,
thing
sir.
you said, in the beginning, in your first slide, you have written that in the definition of basis, you have written that basis should be a non-empty set.
Oh, yes, sir.
Yeah, and
That's incorrect. That's incorrect.
So either you say a non-trivial vector space, that will mean that okay, it is non-zero. Otherwise, you will remove that non-zero.
Yes, sir.
And also this
That's
thing that how to prove that vector space basis of this zero space. Another way can be like you first prove that every vector space has a basis. That will require some machinery, some things using John's lemma and all. And once you know that okay, that every vector space has a basis and basis is a subset of the vector space V, and for singleton 0 you have two sets only, that is empty set and V itself.
Zero. Whole set.
Whole set.
Yes, sir.
But you are proving that okay, this whole set V is linearly dependent. Then you have no other choice that this empty set will be a basis. So
Yes, sir.
it is difficult to write that. I mean, to realize, especially at this stage, that empty span is 0. It's it seems unreal, but that's the truth. But it is hard to realize at this stage. Yeah.
Yes, sir.
Okay. Thank you, sir. You can
Okay,
carry.
sir. Thank you.
Thank you, Alpha.